Welcome! Today, we'll explore problem number 1580, titled Put Boxes into the Warehouse 2. In this problem, we'll dive into the task of fitting boxes into a warehouse, navigating constraints, and optimizing for the best solution. Let's get started. In this problem, you are tasked with placing boxes into a warehouse. You are provided two arrays, boxes, which represents the heights of the boxes, and warehouse, which represents the heights of the rooms in the warehouse. The warehouse is a linear structure, so each room can hold only one box, and a box can only fit in a room if its height is less than or equal to the height of that room. Importantly, you are allowed to rearrange the boxes in any order before placing them into the warehouse. The goal is to determine the maximum number of boxes that can fit into the warehouse. As for the input and output format, you are given two lists of integers as input. The boxes array has a length n, and the warehouse array has a length m, both of which can go up to 10 to the power of 5. The output is a single integer indicating the maximum number of boxes that can be placed into the warehouse. Let's look at an example to understand the problem better. Suppose boxes equals 4, 3, 4, 1, and warehouse equals 5, 3, 3, 4, 1. After rearranging the boxes into the order 1, 3, 4, 4, you can begin placing them into the warehouse rooms. The box with height 1 can fit into the first room with height 5. The next box, with height 3, can fit into the second room with height 3. Then, the box with height 4 can fit into the fourth room with height 4. At this point, the last box cannot fit into any remaining room, so the total number of boxes that can be placed is 3. Therefore, the output is 3. Here's another example. If boxes equals 1, 2, 2, 3, and warehouse equals 3, 4, 1, 2, you can rearrange the boxes as 1, 2, 2, 3. The box with height 1 can be placed in the first room with height 3. The next box, with height 2, can fit into the second room with height 4. Another box of height 2 can fit into the fourth room with height 2. However, the box with height 3 is too tall to fit into any remaining room. As a result, the maximum number of boxes that can be placed is 3, and the output is 3. In contrast, if the inputs were boxes equals 4, 5, 6, and warehouse equals 3, 3, 3, 3, none of the boxes would fit into the warehouse since all the boxes are taller than the room's heights. In this case, the output would be 0. Finally, let's go over the constraints and edge cases to keep in mind. The lengths of boxes and warehouse can go up to 10 to the power of 5. And every value in these arrays can be as large as 10 to the power of 9. You are allowed to rearrange the boxes in any order before placing them, but each box can be placed in at most one room, and each room can hold only one box. Some edge cases include having just one box in one room, where the result depends on whether the box fits. If all rooms are too small to accommodate even the smallest box, the result is 0. Conversely, if all boxes fit into the warehouse, the result is limited by the smaller of the number of boxes or the number of rooms. Additionally, your solution must handle large inputs efficiently to avoid performance issues. To begin, the brute force approach provides a straightforward method to solve the problem, though it may not be the most efficient. The idea is to go through each box and attempt to fit it into every available room in the warehouse. For each box, we check all possible positions to find a valid fit, where the room's height is greater than or equal to the box's height. Once a valid position is found, the box is placed, and we move on to the next box. To prioritize fitting larger boxes first, the boxes are sorted in descending order of height. The process continues until all boxes are placed, or no more valid placements can be made. However, while this approach is simple to implement, it has significant drawbacks. The time complexity of O, n*m, can become a bottleneck for large inputs, where n is the number of boxes and m is the number of warehouse rooms. Additionally, this approach does not take advantage of the inherent structure of the warehouse, leading to inefficiency. Now, let's consider a more optimized greedy approach that leverages both sorting and the warehouse's structure to improve efficiency. In this method, the boxes are sorted in ascending order, from smallest to largest. The warehouse array is then pre-processed to ensure that each room's height is no greater than the minimum of its own height and the height of the previous room. This pre-processing step creates a non-increasing sequence of effective heights, ensuring that only valid positions are considered for each box. By doing so, we avoid unnecessary comparisons. The placement of boxes is performed with 2 pointers, one iterating through the sorted boxes and the other iterating from the rightmost valid position in the warehouse. The smallest box is placed in the largest available room that can accommodate it, and both pointers are adjusted accordingly. This approach significantly reduces computational overhead, with a time complexity of O, n log n plus m, where n accounts for sorting the boxes and m covers the pre-processing of the warehouse array. It also maintains a space complexity of O, 1, making it both efficient and memory-friendly. That said, the pre-processing step in the optimized greedy approach can increase implementation complexity, which brings us to an alternative 2-pointer method. This variation simplifies the process by dynamically adjusting the warehouse structure as boxes are placed, eliminating the need for pre-processing. The intuition is similar: sort the boxes in ascending order so that smaller boxes are prioritized for smaller rooms. 2 pointers are initialized, one starts at the beginning of the boxes array, and the other at the beginning of the warehouse array. Each box is placed in the leftmost valid room, and both pointers move inward. This approach avoids the additional pre-processing step and dynamically handles constraints as they arise. While the time complexity remains O, n log n plus m, the lack of pre-processing makes the implementation slightly simpler. However, the dynamic adjustments required can make this approach less intuitive in certain scenarios. The 2-pointer variation has its advantages, primarily in its simplicity. Without the pre-processing step, there's less upfront work, and the logic is streamlined. It achieves comparable efficiency to the pre-processing-based greedy approach, making it a strong alternative. However, dynamically adjusting the warehouse structure during placement may introduce complexity in reasoning about the constraints. Between these approaches, the pre-processing-based greedy method stands out as the chosen strategy. It provides a clear framework for solving the problem while leveraging the structure of the warehouse to minimize unnecessary checks, making it both efficient and easier to reason about in most cases. The pre-processing-based greedy approach is chosen as the optimal solution for this problem due to its ability to balance simplicity, efficiency, and clarity. Pre-processing the warehouse array allows us to simplify the structure, eliminating invalid positions early and reducing unnecessary comparisons during box placement. Sorting the boxes in ascending order ensures that smaller boxes are placed in smaller rooms, leaving taller rooms for larger boxes. While pre-processing does introduce a small computational overhead, the overall efficiency gain for large inputs outweighs this cost. Comparing the approaches, the brute force method is too inefficient for larger inputs, while the 2-pointer variation is simpler but may require more dynamic adjustments, which can complicate the logic. The pre-processing-based greedy strategy strikes the right balance, making it the most effective and scalable choice for this problem. To solve the problem of placing boxes into the warehouse efficiently, we begin by parsing the input. The warehouse array represents the heights of rooms in the warehouse, while the boxes array represents the heights of the boxes. A critical first step is to sort the boxes array in descending order. This ensures that the largest boxes are considered first. Prioritizing larger boxes helps avoid situations where smaller boxes occupy space that could only accommodate a larger box, making the solution more efficient. Next, we traverse the warehouse array to determine the valid positions for placing boxes. At each position in the warehouse, we update the height to reflect the minimum height encountered so far. This transformation creates a prefix min array, where each position indicates the maximum allowable box height up to that point. This pre-processing step is crucial for streamlining the placement process later. The prefix min array is a powerful optimization because it pre-computes the maximum box height allowed at each position in the warehouse. Instead of repeatedly comparing heights during box placement, we can directly use this pre-computed information, significantly improving efficiency. Now, for the box placement step, we initialize a pointer p to track the current position in the warehouse array, starting from the rightmost position. For each box in the sorted boxes array, we traverse the warehouse from the current pointer position to the left, searching for the first valid position where the box height is less than or equal to the warehouse height at that position. Once a valid position is found, we place the box there, decrement the pointer p, and mark the position as used, if necessary. If no valid position exists for a box, we skip it and move to the next one. By filling the warehouse from right to left, we maximize space utilization and ensure that larger boxes are placed first, avoiding fragmentation. Finally, the algorithm counts the number of boxes successfully placed and returns this count as the solution. There are several key insights that make this algorithm effective. First, sorting the boxes in descending order is vital because it minimizes the chance of larger boxes being left without space. Next, the prefix min optimization transforms the warehouse array to allow efficient height comparisons, reducing the complexity of the placement step. Additionally, starting placement from the rightmost position ensures that we utilize the warehouse space more effectively, as any unused space on the left will not block future placements. It's also important to consider edge cases. For instance, if the boxes array is empty, the output is 0 since no boxes can be placed. Similarly, if none of the boxes fit into the warehouse, the output is also 0. On the other hand, if all boxes fit, the result will be the total number of boxes. These considerations ensure that the solution handles all possible scenarios gracefully. To implement this algorithm, we use a few key data structures. The warehouse array stores the heights of each warehouse room and is transformed into a prefix min array to enable efficient comparisons. The boxes array is sorted in descending order to prioritize larger boxes during placement. A pointer or index variable p is used to track the current position in the warehouse as we place boxes. When analyzing the complexity, sorting the boxes array takes O, m log m, where m is the number of boxes. Constructing the prefix min array is an O, n, operation, where n is the length of the warehouse. Placing the boxes involves traversing both arrays and, with optimizations, takes O, m plus n. Combining these, the total complexity is O, m log m plus n, which makes the algorithm efficient even for large inputs where the sizes of the boxes and warehouse arrays reach up to 10,000. This solution solves the problem of maximizing the number of boxes that can be placed into the warehouse, given both the warehouse's height constraints and the box dimensions. Step-by-step explanation. 1. Sorting boxes. The first step is to sort the boxes array in descending order. Larger boxes are harder to fit, so we attempt to place them first. Sorting ensures we prioritize bigger boxes when filling the warehouse. 2. Adjusting warehouse heights. To simplify the placement logic, the warehouse array is adjusted to ensure its heights are monotonically non-increasing from left to right. Each position in the warehouse represents a room height, and this adjustment ensures that any box that fits in a given room can also fit in all subsequent rooms to the left. This adjustment is done using a single loop that iteratively updates the height of each room to be the minimum of its current height and the height of the previous room. 3. Two-pointer approach. With the sorted boxes and the adjusted warehouse, we use two pointers. Box_index iterates through the sorted boxes. Warehouse_index iterates through the warehouse from right to left. The idea is to try to fit each box into the rightmost available position in the warehouse. If a box fits, its height is less than or equal to the current warehouse height, we increase the count of boxes placed and move the warehouse pointer to the left. Regardless of whether the box fits, we always move to the next box. For counting boxes, a count variable keeps track of how many boxes have been successfully placed. 5. Output. Once we have iterated through all boxes or the entire warehouse, we return the count as the result. Complexity analysis. Sorting boxes takes O, m asterisk log m, where m is the number of boxes. Adjusting the warehouse heights takes O, n, where n is the length of the warehouse. The two-pointer traversal takes O, m plus n. Thus, the overall time complexity is O, m asterisk log m plus n, which is efficient given the constraints. Edge cases. If the boxes array is empty, the result is 0. If all boxes are taller than the warehouse's shortest room, no boxes can be placed. If the warehouse heights are uniform, the solution still ensures correct placement. This implementation is concise, efficient, and handles all edge cases effectively. Here, we start by sorting the boxes in descending order of their heights. This ensures that we attempt to place the largest boxes first, which helps maximize the utilization of the warehouse space. Since Java's built-in arrays.sort method sorts in ascending order by default, we manually reverse the array after sorting by swapping elements from the start and end. Next, we adjust the heights of the warehouse slots to create a monotonic non-increasing sequence. This step ensures that each slot's height is no greater than the one before it, which simplifies the placement logic as we move through the warehouse. After that, we initialize variables, box index to track the current box we're attempting to place, warehouse index to move through the warehouse from right to left, and count to keep track of how many boxes we've successfully placed. The main placement logic begins with a while loop, where we check if the current box can fit into the current warehouse slot. If the current box fits within the height constraint of the warehouse slot, we increment our count to record the successful placement and move the warehouse index one step to the left to check the next slot. Regardless of whether the box was placed or not, we always increment box index to move on to the next box. Once either all the boxes have been processed or there are no more slots available in the warehouse, the loop terminates. Finally, we return the count, which represents the maximum number of boxes that were successfully placed into the warehouse. This concludes the implementation, providing an efficient solution to fit the boxes while respecting the warehouse's constraints. To solve this problem, we begin by analyzing the given example. The input consists of an array of boxes with heights 4, 3, 2, and a warehouse with heights 5, 4, 3, 2, 1. The first step is to sort the boxes in descending order of height, which in this case results in no change as the boxes are already sorted 4, 3, 2. Next, we adjust the warehouse heights to ensure they are not increasing. Starting with the original warehouse array 5, 4, 3, 2, 1, we iterate through each position and modify it to be the minimum of its current value and the value of the previous position. This ensures that each position is no taller than the one before it. However, in this case, the warehouse heights are already in non-increasing order, so no adjustments are needed, and the warehouse remains 5, 4, 3, 2, 1. Now that the boxes are sorted and the warehouse heights are adjusted, we attempt to fit the boxes into the warehouse. We initialize three variables, box_index to track the current box, warehouse_index to track the current position in the warehouse, and count to count how many boxes fit. Starting with box_index equals 0, warehouse_index equals 4, and count equals 0, we iterate through the boxes. The first box has a height of 4, but the warehouse height at position 4 is only 1, so it cannot fit. We move to the next box with box_index equals 1. The second box has a height of 3, but again, it cannot fit into the warehouse position with height 1. Finally, the third box, with a height of 2, is also too tall to fit into the warehouse. As a result, no boxes can fit into the warehouse, and the output is 0. In the second example, the input consists of boxes 4, 3, 2, and a warehouse 5, 2, 4, 3. As before, we start by sorting the boxes in descending order, which again results in 4, 3, 2. Next, we adjust the warehouse heights to ensure they are not increasing. Starting with the original warehouse array 5, 2, 4, 3, we modify position 1 to be the minimum of its current height and the previous height, min 2, 5 equals 2. Position 2 is adjusted to min 4, 2 equals 2, and position 3 is adjusted to min 3, 2 equals 2. After these adjustments, the warehouse heights become 5, 2, 2, 2, ensuring that each position is no taller than the one before it. With the boxes sorted and the warehouse heights adjusted, we now attempt to fit the boxes into the warehouse. We initialize box_index equals 0, warehouse_index equals 3, and count equals 0. The first box, with a height of 4, is too tall to fit into the warehouse position with a height of 2, so we move to the next box by incrementing box_index. The second box has a height of 3, but it is still too tall for the warehouse position with height 2. Finally, the third box, with a height of 2, can fit into the warehouse position with height 2. We increment the count to 1 and move the warehouse index to the next position on the left, warehouse_index equals 2. With no more boxes to check, the output for this example is 1, as only one box fits. In the third example, the input consists of boxes 1, 2, 3, and a warehouse 3, 2, 1. We begin by sorting the boxes in descending order, resulting in 3, 2, 1. Next, we adjust the warehouse heights to ensure they are not increasing. Starting with the original warehouse array 3, 2, 1, we adjust position 1 to be the minimum of its current height and the previous height, min 2, 3 equals 2. Position 2 is adjusted to min 1, 2 equals 1. After these adjustments, the warehouse heights remain 3, 2, 1, as they were already in non-increasing order. Finally, we attempt to fit the sorted boxes into the adjusted warehouse. Starting with box_index equals 0, warehouse_index equals 2, and count equals 0, we begin checking the boxes. The first box, with a height of 3, is too tall to fit into the warehouse position with a height of 1, so we move to the next box by incrementing box_index. The second box, with a height of 2, is also too tall for the position with height 1. The third box, with a height of 1, can fit into this position. We increment the count to 1 and move the warehouse index to the next position on the left, warehouse_index equals 1. With no more boxes to check, the output for this example is 1, as one box successfully fits into the warehouse. To analyze the time complexity of this algorithm, we break it down into 3 main steps. The first step is sorting the boxes array in descending order. Sorting takes m*log m time, where m is the number of boxes. Next, we adjust the warehouse array to ensure its heights are monotonic non-increasing. This adjustment is done with a single traversal of the warehouse array, so it requires n time, where n is the number of slots in the warehouse. Finally, we use a two-pointer approach to match the boxes to the warehouse slots. In this step, we iterate through the boxes in the warehouse, and the total number of iterations is at most m plus n. Each box is processed once, contributing m, and the warehouse pointer moves at most n times, contributing n. So, the time complexity for this step is m plus n. When we combine all the steps, the total time complexity of the algorithm is the sum of the complexities for sorting, adjusting, and the two-pointer approach. Sorting contributes m*log m, adjusting the warehouse heights takes n, and the two-pointer traversal adds m plus n. Among these, the dominant term is the sorting step, since it grows faster than the other components as the input size increases. Therefore, the overall time complexity of the algorithm is m*log m plus n. Now, for space complexity, the algorithm processes the input array's boxes in warehouse directly without creating additional copies, so no extra space is required for the input. Additionally, the two-pointer approach uses only a few variables, such as box_index, warehouse_index, and count, which require constant space. This means the auxiliary space usage is 1. Since no additional data structures are used in this algorithm, the overall space complexity remains 1. Let's now consider the best, average, and worst-case scenarios for time complexity. In the best case, where all the boxes fit into the warehouse easily, such as when the boxes are very small, the two-pointer traversal completes quickly. However, sorting still dominates the overall complexity, so the best-case time complexity remains m*log m plus n. In the average case, some boxes fit while others do not, and the traversal still requires m plus n time. Here again, the sorting step is the dominant factor. In the worst case, no boxes fit into the warehouse at all. Despite this, the algorithm still performs the sorting step in m*log m and completes the traversal in m plus n. Thus, the overall time complexity remains the same across all scenarios, m*log m plus n. To put this in perspective, let's compare the optimized approach to a brute force solution. In a naive method, we would try to fit each box into every warehouse slot individually, resulting in a time complexity of m*n. This is significantly less efficient than our optimized solution. The current implementation improves upon the brute force approach by first sorting the boxes in m*log m, and then using a two-pointer traversal to match boxes to slots in m plus n. This makes the optimized approach far more efficient. Mathematically, we can see that the sorting step dominates the algorithm's runtime because m*log m grows faster than both n and m plus n as the input sizes increase. Therefore, the overall time complexity simplifies to m*log m plus n. Finally, since the algorithm does not use any additional data structures, the space complexity remains constant at 1. When tackling this problem, there are several common mistakes to avoid. First, not accounting for edge cases can lead to errors. For example, scenarios like an empty input, a warehouse that's too small, or boxes that are too large to fit in any room must be handled explicitly. These edge cases should always be validated before finalizing your solution. Another mistake is relying on inefficient iteration. If you simply check every box against every warehouse position, the time complexity can balloon to O(n*(m), which isn't feasible for large inputs. Instead, you'll need to optimize your approach. Ignoring problem constraints is another pitfall. For instance, some variations require that boxes maintain their order or be placed consecutively, and failing to account for these rules can invalidate your solution. Misinterpreting room heights is also a frequent issue. Remember that room heights typically adjust dynamically as boxes are placed, so assuming they stay constant can lead to incorrect placements. Finally, watch out for off-by-one errors in your loops. These small indexing mistakes can cause you to skip valid options or even access out-of-bounds elements, so double-check your iteration logic carefully. Now, let's discuss some key insights that are particularly useful in interview settings. A major takeaway is recognizing patterns across similar problems. Many scenarios involving fitting items, like boxes into rooms, can often be simplified using greedy algorithms or dynamic programming. For this problem, focusing on constraints like decreasing room heights can help you identify the right pattern. Optimization is another critical focus. Interviewers rarely accept brute force solutions, so you'll need to think about how to improve efficiency. For example, you might pre-process room heights or use techniques like two-pointers to streamline your approach. Additionally, it's important to explain the trade-offs between different methods. If you propose multiple solutions, discuss their time and space complexities. For instance, pre-processing room heights may introduce an O(m) step, but it can significantly reduce the complexity of the main logic. Lastly, always clarify your assumptions with the interviewer. Ask whether boxes need to be placed in a specific order or if rearrangement is allowed. Confirming these details ensures you're solving the problem as intended. There are also several related problems that you might encounter, which share similar optimization techniques. For instance, LeetCode 1834 focuses on minimizing operations to move boxes to target positions, while LeetCode 1353 involves maximizing the number of events you can attend. Problems like LeetCode 2076, which deals with processing restricted friend requests, and LeetCode 875, where you optimize Coco's banana eating speed, also rely on patterns like binary search or greedy approaches. In terms of alternative strategies for this specific problem, the greedy approach is a popular choice. Here, you process boxes in descending order of height and place each one in the first available warehouse position that meets the height constraint. While this reduces unnecessary checks, it requires sorting the boxes, which adds O(n log n) to the overall complexity. Another effective method is the two-pointer technique. By sorting both the boxes and warehouse positions, you can process them simultaneously with a time complexity of O(n plus m). This is highly efficient but may require some pre-processing to set up the sorted lists. An additional optimization technique involves pre-processing the room heights. By computing the minimum height up to each position in the warehouse, you can check height constraints in constant time during box placement. This simplifies the logic and avoids redundant computations during the main loop. While this pre-processing adds an O(m) step to your solution, it significantly speeds up the placement process, making it a valuable trade-off. Overall, these techniques, whether greedy, two-pointer, or pre-processing based, offer efficient ways to handle the constraints of this problem, and understanding their trade-offs will help you choose the best approach for a given scenario. Thanks for following along. In this session, we reviewed the put boxes into the warehouse 2 problem, starting with the brute force approach and identifying key optimization areas. Remember, understanding constraints and iterating on solutions are crucial for tackling similar challenges. Stay tuned for more sessions, and happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!